Hi, I'm Michael Pfeifer from Industrial Metallurgists. In this video, I'll explain about how to improve metal fatigue resistance. This is a follow-up to the previous video where I talked about the fatigue mechanism. So fatigue is the localized permanent damage to metals that's exposed to cyclic stress. And that localized permanent damage results in the formation of a crack, and then the growth of the crack, and finally overload of the material. So cyclic stresses are stresses that cycle between a high and low stress over time, as shown here. If the stresses are large enough in the material, then a crack will form and grow. And then when the crack gets large enough, the applied stress to the material gets large enough where any intact material then fails due to overload. And I explained about the fatigue mechanism previously in this blog post and YouTube video, and you can go to them at these URLs. So in this video, I'll discuss the factors that influence fatigue resistance and how we can take advantage of these factors to improve fatigue resistance or do things that reduce fatigue resistance. So there are a number of factors that influence fatigue life. Some of them are shown here. This includes alloy strength, metal's fracture toughness, mechanical design features that are stress concentrators, inclusions in manufacturing defects that are also stress concentrators, residual stress, and surface roughness. So first I'll talk about alloy strength and fracture toughness. So broadly speaking, fatigue strength is proportional to the ultimate tensile strength of a material. The fracture toughness is a property of a metal, and it indicates the ability of a cracked metal to not fracture when there is a crack of a certain length in the material. When a material has a large fracture toughness, then the component can withstand a large crack before there's fracture due to overload. When a material has a small fracture toughness, then it can't withstand this crack size. It can withstand is much smaller compared to a material that has a larger fracture toughness. So for the same applied stress, a metal with a large fracture toughness can withstand larger cracks than a metal with small fracture toughness. Now, this is important for applications where components will be taking out of service during the life of the product. This happens in aerospace and in boilers and in other products where it's known that where there are cyclic stresses and where it's known that components will crack and that cracks will grow, and it's desirable to be able to pull the components out of service or replace them with new components before the crack gets too large and the part fails catastrophically. Strength and fracture toughness are inversely related, as shown in this graph here. You see the fracture toughness versus tensile strength for these different alloys. And for all the alloys, we see the same relationship, that as the tensile strength of the material increases, the fracture toughness of the material decreases. So there's a trade-off between fracture toughness and strength. And it's important that to not just when thinking about improving fatigue resistance, to not just increase strength, because increasing strength can actually have a negative impact on the reliability of a component. So now I'm going to talk about mechanical design features that are stress concentrators. So a stress concentrator results in local stress that's greater than the average stress on the entire component. So with laser marks, notches, abrupt changes in cross sections, and holes in a component, these all act as stress concentrators where the localized stress at these stress concentrators can be greater than the average stress on the material, and these local stresses can end up being above the yield strength of the material. So as a result, you get localized plastic deformation and crack formation at these stress concentrators if the localized stress is greater than the yield strength of the material. And when we have a cyclic stress repeating over and over again, that process takes advantage of these stress concentrators to form cracks and then for the cracks to grow. Inclusions in manufacturing defects and components also act as stress concentrations where the localized stress is greater than the yield strength of the material and where fatigue cracks can initiate. So inclusions in metals are small non-metallic particles that form or are introduced during metal making. This micrograph shows inclusions in steel. Also, you have voids that form during metal casting and laps that form during hot rolling, thread rolling, and forging. Here's a lap right here. All these features in a component act as stress concentrations. So doing things that help minimize inclusions in manufacturing defects is important for parts that will be used in a fatigue application. So minimizing the number of inclusions in the material. So it might require special processing and buying special materials that are known to have a low number of inclusions in other metal making defects. Using processes that that do not result in laps, or making sure that we don't have laps and seams and other defects in the material is important as well. So that goes to process selection as well as supplier selection, and making sure we're buying components from suppliers who can create materials and components that have a low number of defects in them. Residual stress is important because residual stress can add to the applied stress or subtract from the applied stress, affecting whether a crack forms or grows in a material. So residual stresses are locked-in elastic stresses within a material, and these locked-in elastic stresses form in a material during cold working, during heat treating, during welding and other processes. And what happens, you get locked in elastic stresses because one region in the metal is constrained from relaxing by the adjacent region, the metal. And so they can't relax the elastic stresses. So for example, during metal bending, if we bend a metal bar, the outer portion will be in tension, the inner portion will be in compression. And then when the stress is removed from the material, then the outer portion tries to relax, but it's constrained from relaxing by the inner portion, and consequently there's a residual compressive stresses at the outer portion of the bend and residual tensile stresses at the inner portion of the bend. And then in heat treating, there can be phase transformations that result in tensile stresses or compressive stresses at the surface of the material, because as the material cools, the transformations occur, but the material on the inside is trying to grow or shrink and is constrained by the material that's already transformed on the outside. And as a result, we get either compressive or tensile stresses at the outer portion of the material, depending on the phase transformation. So again, you can get residual stresses due to cold forming, heat treating, welding, and surface treatment. So with residual stresses, compressive stresses are good because they subtract from applied tensile stresses and help reduce the stress on the material, and therefore help reduce the chance of forming a fatigue crack. Whereas residual tensile stresses add to the applied tensile stresses that cause fatigue cracks to form and can reduce the fatigue life of a material. So making sure we use the right processing and maybe use stress relief heat treatment and other things to help minimize tensile residual stresses or improve compressive stresses on the surface in order to improve the fatigue resistance of the component. And finally, there's surface roughness. So surface roughness also acts as stress concentrations. The rougher the surface, the greater the stress stress concentration, and the more the fatigue life is reduced for the component. Different manufacturing processes result in different surface roughnesses, and they degrade the fatigue life of the material. There are things that can be done to a component after fabrication to help improve the surface roughness, things like electropolishing and buffing, but having a smoother surface will help to improve the fatigue resistance. And again, the surface roughness acts as a stress concentration where a crack can form in the material. And once the crack forms, it continues to grow with each stress cycle. If you're interested in learning more, consider watching our Preventing Metal Fatigue video. This is a video of a webinar that was taught, and it went into the information I discussed today, as well as in the previous video, and in more detail. It'll help you learn how to prevent metal fatigue and costly failures due to fatigue. And the video is only $39. Also, we offer design and failure analysis help. We help with engineering designs to help reduce fatigue, to improve fatigue resistance or reduce fatigue failures. And we also help with failure analysis. We have a component that's failed due to fatigue to help understand what metallurgically happened and what the stresses were on the material that caused the fatigue crack to form and grow in the material. So that's it. Thanks for watching. Let me know if you have any questions or comments. And so that's it. And good luck with your metals. Bye.